So this is the last video for this section before exam 2. Before I get started in this, let me just quickly review the main things from what we've covered in this second section. We started with probability. And main things with probability is or means add, and means multiply. And then we also talked about independent and mutually exclusive. Independent means if the chance of one thing happening doesn't affect the chance of the other thing happening. So like flipping a coin and rolling a die, they have nothing to do with each other. Mutually exclusive means they cannot happen at the same time. So I cannot be in New York and Utah at the same time. Those two events are mutually exclusive. Then we talked about EV sum, SE sum, and then for percents and for averages. And there was the 6 steps there. So we did expected value, and SE, ooh, that was a C, for sums, and this was mainly with gambling problems. So like you roll a die and get $5 every time you land on a 6 or 1, and you're adding up how many times you get that. That's a sum. With percents, and you will know to do that if you see a percent. So the word percent, or you see percent somewhere. 3 is averages, and you will know to use that if you see the word average. So in the exam 2 info, there's a cheat sheet is what I'm calling it, and it goes through the 6 steps we use with these. You use the 6 steps anytime you see the word chance of something happening, or what's the probability of something happening, or the area under the normal curve, anything like that. You're going to do these 6 steps. Start with the box model all the way down to shade norm. And you can find a summary of all those on the cheat sheet. There will be a video there yet, depending on when you watch this. It might be there, or it might soon be there, where I show you how to use each, when to use each, that kind of stuff. And basically this cheat sheet is going to be very, very beneficial for exam 2, because it just summarizes all the important things from this unit. Typically, people are not allowed to use that cheat sheet on the test, but I'm going to make an open book. So exam 2 will be similar to exam 1 in that it's open book, but you have a time limit of 2 hours, so you can't really spend a ton of time looking for stuff. You do need to study beforehand. But on that note, the final exam, we're gonna do a proctored final exam, which means it's not open note. I'll provide a formula sheet with the final that you can use, but that's it. And it will be proctored through a program called Proctorio, through USU. So we'll actually have to log into our USU Canvas page. So I'll give you guys instructions for that. I'm just giving you a warning right now that your final will not be open book, but I will do the best I can to prepare you for it. We'll spend a whole week preparing for it. So right now, don't worry about a final. Worry about exam 2. But I did want to give you a heads up that is coming up mid-May. Okay, let's actually start this chapter now. So the last thing we need to talk about in this section is confidence intervals. And we're going to talk about confidence intervals with both averages and percents. Researchers often want to know things like what percentage of U.S. citizens live in rural areas, have health insurance, how far does a person have to walk to get to a grocery store? How many minutes do senior citizens exercise? And so on. So there's lots of things that researchers or statisticians are wondering about. With COVID-19, you guys are probably seeing a lot of stats being thrown out there. Some of them are accurate, some of them are not. We're going to talk about how some of those stats you're seeing are developed, or the data behind them that helps them come up with these numbers as we look through confidence intervals. So with confidence intervals, our Gettysburg Address data that we talked about in chapter 23, part 1 video. If you haven't watched that yet, go back and watch that really fast. We decided that the expected value for the length of words in the Gettysburg Address is 4.3 letters. If I were to take a sample of this case sample of 10. So the SE is going to be 2.12 divided by the square root of 10. That's our formula, the standard deviation divided by the square root of the number of draws. Somewhere in here I have my calculator. I don't know where I set my calculator down. We'll just use this one. Okay, 2.12 divided by the square root of 10, 0.67. Okay, what that's saying is we believe that the number of the length for the words on average when we draw out 10 words is going to be 4.3, give or take 0.67 letters. We know the empirical rule, the 68, 95, 99.7% rule. We're going to focus a lot on the 95% rule. Most of the time when we're dealing with confidence intervals, we're dealing with a 95% confidence interval. And what it's saying is 95% of our data should fall within 2 standard deviations. That's what the empirical rule tells us. And so if we include that 2 standard errors away from the expected, we're going to be 95% confident that the actual average is in the within the 2 standard errors. So using your sample average, we didn't actually get a sample average because we're not in class, so I didn't have you do this. So let's just say our sample average was 4.6 letters. And let's say another person had a sample average of 5.2 letters. And another person had a sample average of 3.9 letters. Okay. Let's construct this interval here. The sample average, I guess I don't want all 3 of them, huh? Let's just go with this one. 4.6, and give or take 2 times the standard error. And we got a standard error of 0.67. So that's going to be 5.94. And 3.26. Okay, so from our sample, we can take our sample and then the standard error, that expected error, and come up with a confidence interval. We're going to say we're 95% confident that the true sample or the true average for the number of words is between 3.26 and 5.94, which it is. 4.3 is in between those two words, or in between those two numbers. So on this example, we knew the average. So this was just an example to show that this confidence interval does work most of the time. But what we're gonna do is use sample averages to guess what the true average would be. And it's not so much a guess, it's a statistical process to come up with a confidence interval for where the true average would be. So we can say the true average is somewhere in here without actually having to know what the true average is. And, whoops, pushed the wrong button. This slide's not important. This slide's not important. This slide is important. What this is saying is for a 95% confidence interval, meaning to say I'm 95% confident that the actual average, that I don't know because I can't go out and count every single thing out there, but from my sample, I'm going to say that the actual average is somewhere in between the expected value average, so that's the average you got from your sample, give or take, oh, you know what, I don't like using the expected value average because we don't actually know that, we just know what we get. So the sample average give or take 2 times the standard error average. Okay, so for a 95% confidence interval, you just need 2 things: the sample average and the SE average. So let's do that. A lake contains a large number of fish of a particular type. A simple random sample of 50 of these fish gives an average weight of 4.13 pounds. Okay, there is our sample average. It's not saying all the fish have an average weight of 4.13. There's a large number of fish, so we can't pull every single fish out, measure it, and throw it back in. We're just going to sample 50 fish, and we get a sample average of 4.13 pounds. And the standard deviation of that sample is 2.1. We need an SE, not a standard deviation. So we're going to take this number and convert it to an SE. And the formula for the SE average that we learned in the Chapter 23 Part 1 notes is the standard deviation over the square root of the number of draws. So 2.1 divided by the square root of 50. .296, so I'm going to say 0.3. Okay, from there, we need to find a 95% confidence interval, so all we do is take the formula, sample average, that's sloppy, give or take 2 times the SE average. And I'm saying average there because it said the word average in here. So that's why I knew to do the SE average formula, not SE percent or SE sum. So then we get 4.13, give or take 2 times 0.3. And that gives us 4.13 minus 0.6. 3.53 to 4.73. So we're going to say the true average weight for all the fish in the pond is in between 3.53 and 4.73 pounds. So to write that, I'm going to say I am 95% confident that the actual or true average weight for all fish in that lake is between 3.53 and 4.73 pounds. Okay, this is how you interpret a confidence interval. 95% confident, that does not mean there's a 95% chance of that happening. What we're just saying here is 95% of the data should fall between this range, so we're 95% confident that the true average is within that 95% of the data. So that's what this is saying here. We can be 95% confident that the interval we constructed contains the true population average. This is only true if it is a simple random sample and it is large. So large means more than or equal to 30. So as long as you're working with a sample that's at least 30 data values and it's a random sample, you're good to construct a 95% confidence interval. We do this because it's a lot easier to sample 50 people or 50 fish and come up with an estimate than it is to sample all 10,000 fish in that lake or however many there are. So we do this because it's a lot more or a lot less time consuming, and financially it makes a lot more sense to do this. Confidence intervals give us a plausible value for population parameters. Okay, as I said here, I talked about 95% just a little bit a couple slides ago. Let's keep talking about it. 95% does not mean that 95% of my data is in the interval. That's referring to your data. So the 95% is taking your data information and using it to make a general statement about all data. That's why it has to be large and random, otherwise it's going to be biased. So the 95% is not referring to your data. 95% does not mean chance. If you see the word chance, if there's like a true-false question and it says 95% chance for an interval, you know it's wrong. Because again, it's not talking about the chance that it's in that interval. It's just saying you're 95% confident that it actually is in that interval. Okay, so let's look at another one. A nutrition student takes a simple random sample of 100. So it's random and it's large. Carefully monitors the caloric intake. The average caloric intake is 2,000. Okay, so average is 2,000, and this is for the sample. And the sample standard deviation is 400. Make a 95% confidence interval. So quick reminder, 95% confidence interval always means the sample plus or minus 2 times the standard error. And in this case, we're working with averages because it says average. So it's the sample average plus or minus 2 times the standard error average. Okay, we already know the sample is 2,000. What we don't have is the standard error average. We have standard deviation though. And standard error average is 400 divided by the square root of 100 or 40. because 100 is 10, 400 divided by 10 is 40, yeah. Okay, so we are going to say that is 1920 to 2080. So we are 95% confident that the true average or actual average caloric intake from that large population is between the two numbers we got. So 1920 calories and 2080 calories. Okay. This question, is your confidence interval valid if the histogram of caloric intake is not normal? The answer to that is yes, because the sample done over and over will be normal. And so it doesn't matter so much what the histogram is. What matters is it just must be large, a large sample. And must be random. And again, large means greater than or equal to 30. Is your confidence interval valid if the sample is not a simple random sample? Nope. Okay, here's some true-false questions. I see questions like this on the final every single time I look at a final. So these are good ones to understand. This is definitely Kimberly Hadfield's the one that writes the final. She loves questions like this. So 95% of people in this population have a daily caloric intake somewhere in the interval we constructed. That is false. This 95% confidence interval is referring simply to the average. Average does not include 95% of the people. Average just takes all the people and finds a middle ground. About 95% of the confidence intervals I create this way will contain true average caloric intake. Okay, that one is true. We haven't talked about that yet, but the way we become 95% confident about this is people have done research and found when they do 100 confidence intervals, 95 of them, give or take, contain the true average. That's why they're 95% confident. So that is true. If you do this over and over and over again, 95% of the time it will contain the actual average. So then I can be 95% confident that the interval I created does contain the true caloric intake. That is true. That's why we make this confidence interval. So that is the definition of a confidence interval. I'm going to use CI for confidence interval. About 95% of sample averages will fall within the confidence interval I constructed. Okay, that is false. Sample averages are very different than the true average. So you can't assume anything about other samples. All you can assume is about the full entire population. So confidence intervals only tell about full population, not a subgroup of it. And 95% of simple averages or sample averages will fall within 2 standard errors of the true average caloric intake. That one's very similar to the one right above it. So don't even worry about that one. That one's more complicated than we need. So we just talked 95% confidence intervals, and that 95% comes from the empirical rule where we say one standard error way is 68%, two standard errors is 95%. That's where the 2 comes from in our sample plus or minus 2 times the standard error. But you don't have to do a 95% confidence interval. This table or this stuff right here is referred to as the z-table. And if we look, this area means percent, and this means the z-score. Remember, we calculate z-score all the time by doing the number we want minus the expected value divided by the standard error. So when I say 2, it gives us a 95% area filled in between -2 and +2 standard deviations. Okay, if you understand how this table works, great. If not, that's fine. What you do need to know is you can make a 90% confidence interval and you can make a 99% confidence interval. So we're going to use those numbers. You can make any confidence interval you want. You can make a 78 confidence interval if you want. But we're going to make 90, 95, and 99% confidence intervals. Those are our 3 we go to. So this number right here changes depending on the confidence level. So if the confidence level is 90%, then that number is going to be 1.65. That comes from right here. If the confidence interval is 95%, that number is going to be 2. And if it's a 99% confidence interval, 99%, then that number is going to be 2.6. So this number right here is z. It's the z-score. So instead of saying 2 there, I'm going to say z from now on. And that is our confidence interval formula. Sample plus or minus z times the standard error. You find the sample average or percent. We'll talk percents in a minute. The standard error or standard error average or percent. And then you determine z based off of the confidence level. Most of the time, it's going to be a 95% confidence level. Okay, simple random sample of 80 graduates. It's random, it's large, we're good to go. At a university has an average. Okay, there's our sample average of 23.8 years. So that's their age, with a standard deviation of 4.9. Let's change that standard deviation into a standard error. And it's average still because it says the word average. 4.9 divided by the square root of the number of draws. Typing it into my calculator. 4.9 divided by square root of, oh dear, I didn't type in right. Okay, that is 0.55. And now we are asked to construct a 90% confidence interval. So we have the sample average plus or minus z times the standard error average. We know the sample average is 23.8. We know z, well, it's a 90% confidence interval. 90 is 1.65. And standard error, we got was 0.55. And then whatever that equals, that's your confidence interval. And you would say, I am 90% confident that the true average age is between these two numbers. Okay, 99% confidence interval. Instead of doing 1.65 here, you would do 2.6. So we would say 2.38 plus or minus 2.6 times 0.57. Nope, 0.55. And I got the 2.6 from this number right here. Okay, don't care about that question. Oh, look, here's our formula. Okay, this one's another average question. I think we've done enough average questions, so let's not worry about this one. Let's get to a percent. Ew, 98% confidence. That's dumb. Okay. Confidence intervals for percents are the same thing, same exact formula. Sample plus or minus Z times SE. But this time it's sample percent, SE percent, and Z still the same thing. 90% confidence means 1.65 gets plugged in for Z. 95% confidence means 2 gets plugged in for Z. 99% confidence means 2.6 gets plugged in for Z. Okay, quick reminder, our sample percent and our SE percent. Sample percent will be given to us, or we'll be able to calculate it. The SE percent is a formula we know, and we can look at our cheat sheet. Okay, sorry, hold tight. I'm gonna get the cheat sheet to pull open. There it is. Okay. Ooh, that doesn't look great. Okay, percent. That really doesn't look great. That's what happens when I pull up a Microsoft Word on a iPad, huh? Well, that didn't work so well. But hey, look, the cheat sheet has confidence interval stuff on it and probability stuff on it. Okay, well, I'll just tell you. SE percent is the standard deviation divided by the square root of the number of draws. And the standard deviation, wow, so many arrows, is the square root of the percent of ones times the percent of zeros, where the percent is written as a decimal. Okay, let's start these ones. Oh, look, there's the formula. Okay, a nutrition student takes a random sample of 300 people from Cache Valley and finds that 89% of them say they eat fast food at least twice a week. Estimate the percentage of people in Cache Valley who eat food at least twice a week. Okay, we are finding from a sample of 300, we're going to take that information and make it pertinent to the whole population of Cache Valley. So 89 out of 300 is the percentage we got. So that's going to be our estimate. We can take this sample percent, and that becomes our expected estimate or expected value. So let's do 89 divided by 300 times it by 100%. We get 29.7%. Okay, the standard error. So this is the expected value. The expected value is just the percent you get, unless you're told a number otherwise. The standard error is the square root of 0.297 times, let's do some quick math here, 100% minus 29.7% is 70.3%. So the percent of ones, or the percent of people who do eat out twice a week, is 0.297, or I guess fast food twice a week. The percent that do not is 0.703, divided by the square root of the number of draws. And then we type that into our calculator. Okay, 0.026. And then we have to multiply this by 100% because it is a percent. 2.6%. Okay, this is our sample percent. The estimate is just what we're going to take from our actual sample. This is our SE percent right here. So the next slide asks us to make a 95% confidence interval. So 95% means Z equals 2. We know the sample percent is 29.7%. Give or take 2 standard errors. So we are 95% confident that two times 2.6. The actual percent of people who eat out or eat fast food at least twice a week is in between 24.5% and 34.9%. So we are 95% confident that the true average number of people, or the true percentage of Cache Valley people who eat fast food at least twice a week is in between these two numbers. 90% confidence, the only thing that changes is now Z is going to be 1.6. If we look back, you're out here, 90% is 1.65. Good thing I checked that, huh? So we'll do 29.7%, give or take 1.65 times 2.6. And then you'd calculate that and you'd have your interval. Actually, let's calculate that and talk about the differences there. 29.7 plus 1.65 times 2.6. $29.7 minus 1.65 times 2.6. Okay, notice this is a wider interval. 24.5 to 34.9 covers 10.4%, versus this one covers like 8.5% ish. And it's a bigger interval for this pink one because we're more confident, so we need more options to choose from. If you're trying to draw a certain no, that doesn't work. If you want to be confident that you're going to get the right thing, you want it available to you. And so having 10% available to you versus 8.5% available to you increases the chance that the actual right answer is there. So you'll find that higher confidence means a bigger interval. It includes more numbers. Okay, a May 2000 Gallup poll found 38% of a random sample of this many adults. So we've got random, large, said they believe in ghosts. Calculate the 95% confidence interval for percentage. So we need sample percent, give or take 90% confidence, so 1.65 times the SE percent. Okay, the SE percent is where everybody gets stuck over the years as I've taught this. So let me remind you, SE percent is equal to the percent of ones times the percent of zeros divided by the square root of the number of draws. And then you multiply that by 100%. And notice I didn't fill these two blanks in yet because we don't know the percent of ones. Oh, I'm sorry, we do know the percent of ones. It's 38%. So we know the percent of ones is 38%, which means the percent of zeros is 100 minus 38%. Just the other people, the people that don't believe in ghosts, 62%. Okay, so our sample percent was 38% of people. Give or take 1.65 times, let's type this in. Sorry, just had to make sure this was still recording. Also, sorry this is a longer one. .38 times 0.62. Uh-oh. Let me try that again. Divided by the square root of the number of draws. Move the decimal over twice. 1.5%. So confidence intervals, they're confusing because it's just so much stuff and stats piled on top of each other. But confidence intervals are simply a formula that you plug stuff into. And what makes it confusing is there's a formula and then there's a formula to plug into the formula. So it's kind of like having two problems in one, but don't let that confuse you. It's just a step-by-step process. If you practice it enough, you'll get really good at this process. Okay, we don't need to do any more of these problems here. Yeah, we really don't need to do any more of these problems. So, this homework is due by Friday, May 1st, preferably. Oh, I guess I didn't need to erase the word due, huh? And the assignments. Let's do this. Let's just pull up the assignments on here. So the assignment for chapter 21 and 23 can be found right there towards the middle of the page. Sorry, I can't actually draw on this page, but you see what I'm referring to there. So A, 1 through 5, B and C. And it looks like I got rid of all the review on that one. And chapter 23. So A 1 through 4, B 1 through 6, C 1 through 4. and then 2, 3, 6, and 8. Okay, once you get done with this, so you should start preparing for exam 2. Again, exam 2 is May 8th. I will have available from May 7th through May 9th. Whoops. And you will have 2 hours again on it. It's about the same length as exam 1, but exam 2 always is a little more difficult than exam 1. Just every single time I've taught stats, exam 2 has been more difficult than exam 1. I'm hoping where we get the cheat sheet on it won't be as difficult as usual. But I want you to start practicing not needing the cheat sheet by the time you get to exam 1, because when we get to the final, you won't be allowed to use it.